Hello, everyone. My name is Victor, and I'll be presenting the paper, Practical Double Fetch Protection with Kernel-Fetch Caching. So a quick overview, and then I'll go in more details. In this paper, we focus on defending the kernel against double fetch bugs, which is a certain strain of bugs that happen when a syscall fetches the same data multiple times without proper resanitization after the fetches, giving rise to time to check to time to use style vulnerabilities. And the state of the art, MIDAS, uses copy on write semantics to defend against this, but we saw in our evaluation that we can improve and we can further reduce the performance budget needed for this type of for optimization of for this type of vulnerability. And our idea stems from the observation that during their lifetime, syscalls do not actually fetch a lot of data. So it makes sense to spend some time and develop an optimal approach of caching this data in user space such that we don't have to resurface fetch request from user space and just use the data from the cache. And we implemented this with SafeFetch, and we showed that it has like low performance overhead, less than 5% across a variety of benchmarks. So first, let's understand how a double fetch bug in the kernel works. Consider a thread that has access to some user space data. The thread calls a syscall. It transcends into user space, into kernel space. Sorry. It first fetches the data, and after this fetch, it also sanitizes the data, makes sure that everything is okay. But for some reason, it might need to fetch the data again, and it uses the data without actually checking whether the data has changed. And if there's a thread that also has access to this data and modifies it in between these two fetches, you have like a time to check to time to use attack, because the second fetch might operate on potentially malicious data. And MIDAS, the current state of the art, found an interesting approach to actually defend against this attack. So when the first fetch happens, MIDAS marks this page read-only. So like the entire page where this data resides is marked read-only. And the second fetch just reads from this page. If we have like a thread trying to modify concurrently this page, then you're going to have like a page deduplication process, like a page deduplication, and the thread will modify a fresh copy of this page, while the syscall does not actually see this modification anymore. So by construction, this actually defends against double fetch bugs. But in our studies, we noticed that in some scenarios, this approach may have non-trivial overhead. And like, as an example, we discuss about this more in the paper, but as an example, in multi-threaded scenario, this might pose an issue because threads actually have to communicate between each other when they actually do this modification to the pages, because they share the same page mappings. So we took a different approach to this problem. We profiled the kernel to understand against different workloads. We wanted to understand what are the patterns, the fetch patterns of syscall execution. And we noticed like some interesting facts. Like for example, in our profile, most of the syscalls do not actually fetch data. So 60% of syscall execution do not fetch user data lore from our profile. And furthermore, on average, syscalls do not fetch far less than a page. Like, take a look at this picture. Here we see like a histogram of all the execution in our profile, and like they're basically clustered based on the total amount of data that they fetch. So from this image, I'm not sure if it's really clear, but I'm going to highlight 90% of the syscalls fetch far less than a page. So like a page-granular approach might not be actually necessary for this defense. But if you look even closer, 66% of the syscalls actually fetch even less, like 64 bytes. So based on this observation, we thought that using caching, we can actually develop like a defense that is performance efficient. And this is essentially what we do with SafeFetch. So SafeFetch essentially maintains during the execution of a syscall kernel-side fetch, cache for this syscall. On the first fetch, it uses the virtual address, user space with the virtual address to index this data within the cache. And then on the second fetch, it essentially uses also a virtual address to find this data in the cache and service it from the cache, therefore eliding the need of actually an extra fetch, and by construction eliminating the double fetch, because now any modification to the user space data is not viewed by the syscall. And based on our performance profiling results, we also pick the optimal structure to actually do cache queries for our defense, but as well we decide how to manage the cache. And this contains information such as how we provision the cache and how we destroy the cache efficiently, given that this cache has a really small lifetime. So a syscall is quite fast. And after the syscall ends, the cache is not needed anymore. You need to actually destroy it. So essentially, based on our data, we make the observation that the vast majority of the vast majority of syscall only fetch a small amount of individual buffers from user space. While only in isolated cases, we actually would need a cache where we actually have in the orders of thousands of elements in the cache. So we chose as a solution, there were different, opportunities, but as a solution, we chose an adaptive structure. Our data structure starts as an ordered linked list, so range queries are done on an ordered linked list. But after the cache reaches an experimentally chosen number of elements in the cache, we pay the extra performance overhead of transforming the linked list into a perfectly balanced red-black tree, because the red-black tree is far more efficient when dealing with cache searches when you have a lot of elements in the cache. And for cache management, first, to make clear, for each object that we fetch in the cache, we keep a metadata object, which contains information such as user virtual address and length, which we use during searches, in the cache searches. And the metadata object contains a pointer to the actual data. So considering that the cache is managed as a red-black tree, in order to actually provision and manage the cache efficiently, we make use of a region allocator. The region allocator services metadata and data chunks. And essentially, metadata are chunked together in metadata region chunks, while data objects are crammed in a data chunks. We could have merged everything in the same region, but the whole idea here is to actually cram together metadata in a single chunk to actually have better CPU cache utilization. Because in this way, if we touch one single metadata object, we touch a lot of metadata objects, and these are really important for cache searches. So we need them together. Now the process of destroying the cache during a syscall exit is simply releasing these chunks back to the region allocator without actually going through each and every object for the allocation. And using the region allocator, you can read more in the paper, also gives us the opportunity to actually reuse some of the storage across system calls that are called from the same process. It's more in detail in the optimizations further optimization that we do for this defense. Now, to move to results, we evaluated SafeFetch against Midas on LM-Bench, which is a kernel-intensive benchmark, tests a lot of important syscalls, and we noticed that the overhead is lower than for Midas. For SafeFetch, 4.4 geometric overhead across all syscall benchmarks compared to 35.9, which essentially shows that on really kernel-intensive workloads, the caching technique is more efficient than modifying page permissions. Furthermore, we tested it also on OS Bench, which is yet another micro benchmark at a higher level. It tests libc wrappers around specific kernel subsystems, like it tests like process and thread creation, memory allocation, file creation. And here we have like an order of magnitude less overhead. And here we wanted to understand why this happened. We noticed that the problem here was that Midas scores okay on most of the benchmark, but on the thread creation benchmark, the results are a little bit lower. So we investigate this scenario more in the paper. We discuss why this happens. We also tested on real-world applications from the USENIX suite. We chose like a varied enough workload, we believe. We had like kernel-intensive applications such as IPC mechanism, more CPU-intensive mechanism. We wanted to see like if like we don't do any double fetches, is there any performance overhead due to SafeFetch, but also like single process, multi-threaded, multi-process applications such as like the NGINX and Apache web servers. And here we perform we have like slightly less overhead than Midas. While we looked at the benchmarks, we noticed that this is mostly because like on web servers, we perform slightly better, like 2% overhead on both NGINX and Apache. You can read more about this in the paper. And to conclude, I presented SafeFetch, nearly comprehensive protection against double fetch bugs. It has less than 5% geometric overhead across a variety of benchmarks. There are like other optimizations that we consider interesting, and you should, if you want to read them in the paper, such as our zero copy optimization for really large copies user fetches. And we also showed that it works on a proof of concept bug with, yeah. This is our QR code to our code base, and here you can find links to also the paper and our artifact evaluation. Thank you very much.
Thanks a lot.